Hi, in this lesson I'm going to talk about London dispersion force. Now, who's the scientist who discovered the force? Well, it was the German theoretical physicist Fritz London. Now, what is that force? Well, London dispersion force is an intermolecular force, which is a weak force. It occurs between molecules and atoms, and it is weak, as we said, and doesn't occur for long terms. It occurs for short terms. Okay, now let's take an example for London dispersion force. Without the force of London dispersion force, we won't have noble gases in a liquid form. Let's take an example of helium. Here we have two protons. This is an atom, this is an atom. We have two protons and two protons here, two electrons and two electrons. And what is that? Well, that's the cloud of electrons, because we know electrons, we don't know where are they located, but we're just saying that imagine it's here and it's here. So we cool them down and they get closer to each other. Now what happens is that there's a force that will connect them. It will hold them. So that force is known as the London dispersion force. But at the same time, we're going to have a temporary dipole-dipole. So let's talk about first thing the London dispersion force. Well, they get closer to each other. What happens is that those electrons that are located here, for example, will get closer and they'll get attracted to the proton of that helium. So, of course, opposite charges attract and same repel. That's according to Coulomb's law. Then that electrode, negative charge, will repel those negative charges. At the end, what will happen? The molecule change shape to look like something like this. Let's shift this a little bit. So to look like something like this. Also here. And what will it form? We said temporary dipole-dipoles. So to look like something like this. Now, what is the London dispersion force? First thing, let's not forget to put that delta positive here and delta negative here, and delta positive here, and delta negative here. We're going to talk about those later in another video, which is about the dipole force. Those are delta negative and the delta positive. Whenever we're going to have a temporary dipole-dipole force, they should have the molecule or the atom should have a positive and a negative side charge at the end of the sides. Okay, so what's happening here? As soon as we have that temporary dipoles, we're going to see that we're going to have here an attraction. They're holding each other, but not for a long time, and it's not that strong. And that is the London dispersion force. It's going to stay for a little bit of time, and it will disappear later. So this is the London dispersion force. So it doesn't stay for a long time, but still it can hold the atoms or molecules next to each other. Well, for helium, it will hold those helium atoms next to each other to form that liquid helium, and of course it should be cooled down always in a cool temperature. Now we talked about the London dispersion force. Let's talk about what makes it stronger. Well, we know it's a weak force and it doesn't occur for a long time or long term. What makes it a little bit stronger? Well, we're going to have four things. First thing, it's going to be the contact area. Second thing is the polarizability, and increase in molecule size, and pi bonding. Let's talk about them. Let's talk about first thing the contact area. Imagine we have two different molecules, but they're made out of the same element. Same elements. So that's the first one. Wait. It looks a little bit clumped. The second one is like this, for example, a little bit wider. Let's call this molecule X and this is molecule Y. Well, because here we have more surface area, we're going to have more contact area. So that means that the London dispersion force here will be stronger in the molecule Y rather than X. Plus, it will have a high boiling point and molecule X will have low boiling point. Now this is for what? For the contact area. What about the polarizability? Now what does it mean? Polarizability means it's the ability to form instantaneous dipoles. So that's polarizability, or also known as squishiness or squashiness. So an example is proteins. I can't draw them because I don't want to make a wrong picture or a fake picture about proteins. But a good example for the increase in the London dispersion force in the protein will have polarizability. Now, what causes polarizability? It is the increase in the number of electrons. So when that happens, also we're going to have increase in molecule size. So when we increase the number of electrons, so it will create that number of electrons. We're going to have a lot. Sorry, we're going to have a number of electrons that are a lot. Then going to create that it's going to create that polarizability, and also in the increase of the molecule size. So it will be bigger, and the London dispersion force will be greater. Now the last thing is pi bonding. What is pi bonding? Well, pi bonding, as we know, that we have something called as what? The orbitals. It's the pi bonding is when you have orbitals overlapping. Again, when orbitals overlap, we're going to have stronger London dispersion force. So that's about the points that increase the strength of the London dispersion force. So this is all about our lesson for today, and I hope it is useful. And don't forget, I'm going to leave here, I think, a link of the next video, which is about the dipole-dipole forces. So this is all about our lesson for today, and I hope it is useful.